the 200-hour autonomous marathon. Figure 03 recently completed a 200-hour continuous autonomous operation test, maintaining a sub-3-second cycle time per package. This is not a cherry-picked demo. The robot sorted 88,000 items on a live, unedited stream last month to prove mechanical and software endurance. The performance data shows a 0.5% error rate, a figure that suggests the gap between lab prototypes and industrial reliability is closing. But physical endurance is only half the battle. The real constraint is how the control loop handles the space between frames. The high-frequency jitter problem. Traditional robotics controllers are bottlenecked by discrete inference loops, usually running between 50 and 400 Hz. This frame-based approach forces the robot to essentially guess the path between point A and point B, leading to the microstutters and jitter common in earlier humanoids. By adopting continuous time architectures, the control stack in Figure 03 solves for the entire motion trajectory as a dynamical system rather than a sequence of snapshots. Solving this jitter meant moving away from static snapshots to a continuous time architecture, the ODE solution for fluid motion. The underlying mechanism relies on ordinary differential equations to define how neural states evolve over time. Unlike standard transformers that process data in fixed tokens, these liquid-style networks adapt their internal time steps based on the complexity of the input data. This allows the robot to maintain high-fidelity control during complex tasks without the compute overhead of a brute force loop. However, there is a trade-off. While continuous models excel at fluid manipulation, they often struggle with the rigid procedural precision needed for symbolic logic tasks. This mathematical shift is what finally enabled the production scale seen in the California facility, the signal under the noise. This pivot to continuous time systems represents a fundamental re-engineering of how physical agents interact with the world. By integrating differential equation solvers directly into the Helix architecture, Figure 03 avoids the latency spikes that typically cause hardware failure during high-speed manipulation. This transition from discrete sequences to fluid dynamics, as discussed in the control loop and ODE sections, allows for a 2.6-second throughput that matches human warehouse performance without the jitter of earlier systems. For builders, the message is clear. The focus is shifting from perfecting individual frames to optimizing the global flow of the policy. The success of this 200-hour endurance test suggests that the bottleneck is no longer the AI's ability to reason, but the thermal and mechanical limits of the hardware. The real indicator to watch is the first-pass yield on the bot queue line. As production hits 1 unit every hour, the data flywheel for these models will provide the volume needed to move beyond the warehouse. Look for the full shift deployment at the Spartanburg plant this autumn as the final benchmark for this approach. Subscribe for more